excited to present our recent work titled EdgeLoRA today. It's an efficient multi-tenant large language model serving system on edge devices. This work was done by Case Lab from the University of Maryland. Okay. Large language models are behind a lot of exciting AI applications as we see today, especially in areas of healthcare, smart homes, and IoTs. They help systems become more intelligent and more aware of context, whether it works on text or other modalities. Now, as more of the AI applications move to the edge, things are changing. Devices like smartphones just direct use the HDMI? Sure.
Okay. No,
it works. Now, as more of the AI applications move to the edge, things are changing. Devices like smartphones, laptops, AR/VR headsets, and even cars need to run this model locally. That means this model should work in real time, protect user privacy, and adapt to personal preference. Take a smart home, for example. You might have a voice assistant answering questions, a thermostat figuring out the best temperature, and a camera system monitoring activities, all at the same time. And each of these may rely on a specific models. But there is a challenge. Edge devices doesn't have unlimited resources. Memory, computing power, and battery life are all limited. So running multiple models at once can really push those limits. The most naive solution to serve multiple models on one device is to just deploy them into the memory, but it's very memory intensive and can only fit for a little number of models. For the adapted model solution, we could only hold one base model and serve a lot of adapters at the same time. Now, let's take a closer look at the specific problems that EdgeLoRA is designed to solve. First, choosing the right adapter manually is a real headache. It takes time, it's error-prone, and if you pick the wrong one, the system can behave inefficiently, or it just gives you a wrong answer. This motivated automatically adapter selection. Then, there is an issue for adapter swapping. This isn't cheap. Every time you want to load a new adapter into the memory, it adds delay. And that's especially painful on devices who doesn't have a lot of memory or cannot handle tasks in parallel. So this needs intelligent memory management. And finally, the current tools we have, like Lambda-CPP, weren't really built for this kind of setup. They don't handle multiple adapters very well. They struggle when it comes to concurrent and diverse workloads. This requires efficient inference. Put these things together, EdgeLoRA comes out. It's built to tackle these challenges in a way that's both stable and efficient. At the core of our system is something called LoRA, which stands for low rank adaptation. Rather than fine-tuning all the weights in a model, LoRA frozen the base model and adds a small trainable low-rank matrix into some layers of the model, which could be seen as the gradient of original weight matrix. This cuts down the number of trainable parameters by a factor of 1,000 to even 10,000 times. LoRA is really popular for domain-specific tasks, like in medical, legal, or scientific applications. That makes it a great fit for lightweight on-devices adaptation, perfect for EdgeLoRa's multi-tenant use case. During inference, you have two options. The first, you could just merge the LoRa matrix into the base model directly. That will give you the fast speed for inference, but it will use a lot of memory, especially when you want to run in several models at the same time. Or you can just apply the LoRa weights separately during the inference. That means you could save multiple adapters at the same time, and it's very memory friendly, but it takes some compute overhead. So that's a trade-off. But EdgeLoRa is designed to make this balance work smoothly. So how is the EdgeLoRa actually structured? It's built on top of Llama.cpp, but we have added two key components to make it ready for multi-tenant inference. First, there is the server manager, which handles incoming requests and decide how to schedule them. Then there's the computing backend. It takes care of the actual inference. When a request comes in, it goes through a slot-based state machine. The steps look like this. First, the adapter router picks the right LoRa adapter. Next, the adapter memory manager handles loading into memory. And finally, it moves to the batch inference for real computing. By tightly integrating these steps together, EdgeLoRa achieves fast, efficient performance. Memory is limited. One of the standout features for EdgeLoRa is adaptive adapter selection. Instead of asking users to manually select the right adapter for every task, we have built a smarter system. A trained multiple label classifier looks at the prompt and figure out which adapters are the best fit based on the confidence scores. That means each request gets matched with the most appropriate adapter automatically. And here's the clever part. It also prefers adapters that already loaded in the memory. So if the right one already there, it could skip the loading pass and saves time. It's fast, efficient, and when you add more adapters, it just scales with you. And memory is limited on edge devices, so managing it where it's critical. That's where EdgeLoRa's heterogeneous memory management comes in. First, we use LRU cache. It keeps the most recently used adapters in the memory, so they are ready to go when next time needed again. At the same time, we have pre-allocated the memory pool. That means each adapter gets its pre-reserved block of memory, so there's no allocation delay or memory fragmentation when it's time to load it. By combining these two strategies together, EdgeLoRa makes the most of limited memory and keeps the system scalable, even when the number of adapters increase. As the animation shows, when an adapter memory manager wants to load a new adapter, it would evict the LRU one and load the new adapter into the reserved memory block. Inference efficiency is another major problem. EdgeLoRa introduced a clever batch strategy. It decomposes the batch into two parts. The first is base model computation, and another is adapter-specific computation. Requests with different adapters still share the base model batch, while the adapter computation could be grouped together separately. This dramatically improves the throughput and the better device utilization, even under very heavy and diverse workloads. Technically, we built a prototype of EdgeLoRa, built it on Llama.cpp, implemented in C++ with a JavaScript front end for evaluation. It used a slot state machine to manage concurrency. Each slot moves sequentially through adaptive selection, prompt decoding, and generation. Despite its advances, overhead remains minimal. Shared memory pool, efficient GPU usage, and the streaming design keeps latency under control. We use 3 different types of hardware: Jetson AGX Orin, Jetson Orin Nano, and the Raspberry Pi 4, covering a wide range of computing capability. This allowed us to benchmark performance across both high-end and highly resources-constrained edge platform. For models, we evaluate Llama 3.18 billion, Llama 3.23 billion, and OpenELM 1.1 billion, using both 8-bit and 4-bit quantization. Each model was paired with multiple LoRa adapters to simulate the realistic multi-tenant scenarios. We follow the synthetic workload setting as AlphaServe and EdgeLoRA does. It just uses the gamma process to produce the dynamic multi-tenant workload. In terms of metrics, we focus on the throughput, latency, and the service level objective attainment, while also measuring scalability and energy consumption. This gives us a comprehensive understanding of how EdgeLoRA performs under varying settings. Real-world testing across devices shows big wins. EdgeLoRA achieves 2 to 4 times higher throughput compared to vanilla Llama.cpp, even while managing thousands of adapters. And we constantly meet sub-second first token latency, maintaining over 98% service level objectives. And the energy consumption is also reduced, making EdgeLoRA more sustainable for edge deployment. This result shows that efficient multi-tenant large language model serving at scale is achievable on edge devices. So what's actually driving these performance gains? That's where the application and the variant analysis comes in. First, let's talk about adaptive adapter selection. This smart routing only adds a tiny bit of latency, but in return, it will give a big boost of cache efficiency. So it's very worthwhile trade-off. Next, we look at the slot scaling. As we increase the number of slots, batch processing becomes more efficient, and the throughput keeps increase until a point. Once you hit the optimal level of concurrency, the benefits stop, mostly due to the resources limited of the devices. And finally, we test DVFS and different energy modes. Naturally, when we lower the power setting, throughput suffers a hit, but EdgeLoRA is designed to adapt, so it still performs very well, even under constrained power budgets. All in all, this experiment shows that every part of the system is pulling its weight, and together, they make the EdgeLoRA more efficient and robust. In summary, EdgeLoRA provides an end-to-end system for multi-tenant, efficient large language model inference system on edge devices. It integrates adaptive adapter selection, heterogeneous memory management, and batch inference to achieve high performance and energy gains. Looking ahead, we are excited to explore more types of adapters, tailor some optimization to specific hardware, and also we'd like to support some federated deployment on the edge. Okay, that's all. And here is the link of our paper and code, as well as my email address. If you have any question about the paper, please contact me. Thank you.
All right, let's thank our speaker. Really excited to see that the code is also public, so we all can build on top of it and keep making more progress. So yeah, questions?
Okay, very solid work and a great presentation. This is Lemi from Hong Kong PolyU. I have a question that, so it seems that the selection strategy of LoRa adapters is based on a trained router. So I'm curious that what is the difference between your work and mixture of experts? Because in mixture of expert, we still need to, we also train a router and it selects some network layers to continue the inference? Yeah.
Thank you. Good question. Mixture of experts is trained on the in one round or multi-round using the same data, but for different LoRa adapters, it could, for example, one LoRa adapters could train for this task, use a specific data set, and another LoRa adapters could be trained in another task. So it's specific to task, but for MOE model, it's trained with a whole data set, and the router is trained with the experts.
Okay, so your work is more flexible than MOE. Okay.
Yeah.
Okay. Thank you very much.
Thank you.
Thanks for the presentation. I'm Peng Cheng from Purdue University. So I have a question. So during inference, do you run both the base model and the adapter on the embedded GPU, or just the adapter part?
We run experiment on 3 different devices. The first 2 JSONs have GPU, and I run both base model and adapters on the GPU. And for the Raspberry Pi 4, it doesn't have GPU, so all computation runs on CPU.
Yeah, thanks. And my second question is, you mentioned that there's a small overhead. Is that from the router part?
The overhead comes mainly from the router because when a prompt comes in, it has to process the prompt first, and it will add the latency at the same time with prompt decoding. So that, but we use batch inference to hide this latency.
Yeah, thank you.
Thank you.
I had one question. So you mentioned this cool idea of adapter managers. Do you think in the future these adapter managers will be in hardware in some way?
We don't have such plan, but I think hardware would make this process more quick.
Of course. All right, let's thank our speaker again for an amazing presentation.